so I want to continue on with the example that we left off on. And remember what we're doing here is the one sample Z interval from U. All right, so on this one we have 36 cans of soda are randomly selected, so we have a simple random sample of size 36. We find out the mean is 11.95 ounces. We're also going to assume that the population standard deviation for some reason is known to be 0.02 ounces. So a good thing to do at this point, before you proceed any further, is to write down what's what.
N is 36.
Yeah, 36, the sample size is usually the easiest to pick out here. So N is 36. 36 is not the number, it's the letters. You guys got it, right? So we're okay with that? We've got this 1195 here. So we take a sample and we find out the mean is 1195. So that means the 1195 must be what?
X bar.
X bar. So 1195 is X bar. And then it says assume the population standard deviation is known to be 0.02 ounces. So the 0.02 is... Okay, so everybody okay with what we've got up here? Okay, so number one, what's the point estimate from mu? So, again, the way I phrased it yesterday was somebody puts a gun to your head and said, all right, what's mu, what's your best guess? Well, your best guess is what?
11.95.
It's X bar, which is 11.95. It's probably not right, but so the point estimate is just 1195. Remember, a point estimate is just a single value, single number to estimate some parameter. All right, number two, create a 99% confidence interval for mu. So let's do that on the sheet. Okay, so we only have one procedure at this point, so that's probably going to be the one that we're going to use. Remember, the assumptions are X bar normal, simple random sample. X bar normal, we can talk about that in a moment. SRS, that was given in the problem. But the big one that's going to help you differentiate when to use this interval versus the next one we're going to use is, we know sigma, right? To use this procedure that we're talking about right now, you have to know what sigma is, and that was given in the problem, so that's what we're going to use. So we're going to use this Z procedure. So the formula is X bar plus or minus the Z critical value times sigma over the square root of N. And we know that X bar is 11.95, so we can plug that in. What Z critical value should we use? Or maybe a better question is, what tells you which Z critical value to use? Right, it's the confidence level, right? It's the confidence level. And yesterday I think we did a 95% confidence interval, or maybe 9, I can't remember which one we did. But if you do 95%, it's 1.96. If you do a 90%, it's 1.645. For 99%, what are we going to use? 2.576, right? And you could verify that for yourself if you really wanted to. You just would go to your Z table and say, okay, well, which values capture the middle 99% on a Z curve? And you would find out that it's between 2.57 and 2.58, but it turns out it's 2.576. All right, so then we'll multiply by sigma over the square root of N. Sigma is 0.02. And N was 36, right? So this should give us our 99% confidence interval. Now, one thing to point out here, this thing that we add and subtract, this bit right here. So if I were to take 2.576 times 0.02 divided by the square root of 36, what do I call that piece that I've circled there?
Margin of error.
It's the margin of error. So if anybody ever talks about the margin of error in a confidence interval, They're just talking about the piece that you add and subtract. So this is the margin of error.
Thinking about add and subtract, I guess.
Because it's plus and minus, right?
Yeah, well, yeah, but I mean, I guess you'll get to how we do that.
Yeah, I think we did that yesterday, didn't we?
Yeah,
So
I-
to get the two endpoints, you take this minus this, and to get the right endpoint, you take this plus this.
Oh, okay.
That's all you do. The plus or minus just means you do it once with a plus and do it once with a minus.
And so that way you get both endpoints.
You get both endpoints.
That's-
Yeah, so that entire thing you add and subtract, 2.576 times 0.02 divided by the square root of 36, that is the margin of error. And then if you want to even go a little bit farther with things, to be more specific, that piece right there, the 0.02 divided by the square root of 36,
Here's the standard.
that's the standard error. Call that standard error. So anyway, take a calculator, and I've got one here. So let's calculate the margin of error by itself first. 'Cause I think in the homework, I think it actually asked for that. So 2.576 times 0.02 divided by the square root of 36. So it's 0.0086 basically. I did that right?
I got syntax error, so.
Yeah, like what I got now.
That's syntax error, so.
You got to divide by the square root of 36. So just divide by 6. Okay, so the margin of error is 0.0086. If for some reason we wanted to know what that was, that's what it is. And then to actually calculate the endpoints in the interval, to get the left endpoint, we'll take 1195 minus this. To get the right endpoint, we'll take 1195 plus that. So do we do it once each way? And so if we take 1195 minus 0.0086, get 11.9414. And the right endpoint, we get 11.9586. So the way we would word this is we're 99% confident that this interval contains mu. So basically that's our interval estimate of where we think mu is. It's somewhere between 11.94 and 9414 and 11.9586. Okay, so that's number one, or I'm sorry, that's number two. That's the 99% confidence interval. Number three says show that you checked the proper assumptions. Remember, there's three assumptions that go along with this. The first assumption was x bar is normal, right? We have to have x bar to be normal in order to use this procedure. Are we okay with that? Remember, there's two ways that you could have x bar be normal. Notice I didn't say the population normal. I said x bar normal, because there's a subtle difference there. X bar could be normal in one of two ways. Either you've got a big sample, or you've got a normal population. So in our case, did I tell you the population was normal? No, nowhere in there does it say the population is normal, but we have a fairly large sample, don't we? So maybe we can appeal to the central limit theorem and say we have a large sample. And that's taking advantage of the central limit theorem. All right, number two was simple random sample. At least I think that's the order I had it in. And that was given in the problem, right? Just given. Yes, I think it was. And the third one is that sigma's known, and that was given also. All right, so we're good in terms of our assumptions. Any questions on the assumptions? Carl? apologize for the handwriting. G-I-V-E-N.
So, something around the sentence given the sequence given.
Yeah, it was just told us in the problem.
Then I got you.
Number 4, it says, is it reasonable to think that mu is 12? Now remember, we're talking about soda cans here. We randomly selected 36 soda cans, and we're measuring the amount of soda in a soda can. So what we want to do maybe is check to see if we think that, you know, is the average amount in a soda can really 12 according to our data?
No.
Yeah, so remember what we do is think about the number line. So this is the number line. Here's 12. Here's our interval that goes from 11.9414 up to 11.9586. All right, so this is our confidence interval. We think mu is somewhere between here and here. What do I call this 12? What did I call that yesterday? Do you remember that?
The NV.
No, I wasn't. The MVD was the distance between the two. Remember I called this a mu claim. You called that a mu claim. So, you know, so the company says, oh wait, our soda cans, on average, we put 12 ounces in those things. That's what the company's claiming. So the company says we put 12 ounces on average in those things. So maybe what we do as consumer groups, we go out and say, all right, well, let's test that claim. We take 36 cans. We measure the amount in those 36 cans, and we come up with a confidence interval for the true average between here and here. So is it reasonable to think that mu really is 12 according to our data? No, right? We'd say no. If we think that it's different, how different do we think that it is?
12 minus 11.
Right, that's the MVD. The MVD is this distance right here. The MVD is the distance. We think on average they're underfilling their cans. How much do we think they're underfilling their cans on average by? And the answer is this distance here. So we call that the MVD. MVD stands for minimum verifiable difference. And the MVD is 12 minus 11.9586. And so the MVD turns out to be 0.0414 ounces. And so putting this all together, we'd say, okay, well, we do have evidence that the company's underfilling their cans on average. We think they're underfilling their cans by at least 0.0414 ounces. Now, it could be more, because we think that the true average is somewhere between here and here. So it could be more. All right, does that make sense? Any questions on that? Any questions on any part of the problem here? Okay. Now the next problem says 14 bolts are randomly selected, and you kind of go from there. What I'm going to do is I'm going to leave this for you guys to do, and then at some point I'll just put the answers up on the board, and you guys can compare what you get with what I put up there. Okay. So this one is, I'm not going to collect it or anything like that, but it'd be a good idea to do and kind of see if you're on the right track. Okay. Any questions on anything?